Welcome back, everyone. How's it going with your daily life and with your weekend? All right, so today we will we will do another aspect of the statistic, which is logistic regression. And as normal, I always review and always have a discussion before we move to the next session with the main point of our discussion. So the logistic regression, okay? Logistic regression is a kind of GLM that use the binomial methodology. So it is in the group of the GLM. And I will ask in what way that we can use the logistic regression and what are the response variable and what are the predictor that we can use the logistic regression. All right. So please be ready and please connect to the next video so that we can use the logistic regression together. Okay. Can we use the chi-square to do comparison or association? Okay, association using the so-called ordinal data. Can we? It was nominal data, right? It was nominal data that we practiced yesterday. Was it? I'm right? We use nominal. But for qualitative data, we have both nominal and ordinal. So my question is, can we use the ordinal data to do comparison, to do association using chi-square test?
Maybe yes, sir.
Okay, Brian said maybe yes. How about other?
Yes, sir.
Okay, Elliot said yes.
Yes, sir.
Jesse, okay, yes. Others? Anthony?
Yes, sir.
Okay, yes. And I don't see Donna here. Oh, Janeline, not yet here. Okay. All right. Of course, because they are qualitative data. But just know that if the ordinal data here, it has like more than 5 order, like 1, 2, 3, 4, 5, up to 6 or more than 5, then we can consider this ordinal to be quantitative and therefore use the quantitative analysis instead. But if the order is less than 5 or maximum 5, we can do comparison, okay? We can do association, we can do correlation using the ordinal data as well. Like we discussed in the very first session that ordinal data is a semi-quantitative data and the qualitative data. It's in between. So sometimes it is considered to be quantitative for the analysis, and sometimes they consider to be qualitative for the analysis. All right. So it is situation-based, context-based for the ordinal data. But for the nominal data, it is for sure for qualitative analysis. And for scale data, it is for sure for quantitative analysis. All right. But for nominal data, it depends. If it is too many orders, then we may consider to be quantitative. If it is like 4 or 5 or 3 to 4 to 5, we can use for qualitative analysis using chi-square to do comparison, using square to do the correlation or association. Okay, that is nominal. All right, coming back to the next objective, we are doing the assessment or the effect of one variable to on another variable. We're using the logistic regression. And in logistic regression, okay, we discussed yesterday the mainly practice idea or the main practice, the worldwide practice, the wide implementation of the logistic regression is to fit the model using all the quantitative independent variable, okay, to fit with or to predict, to test or to predict the outcome, which is nominal. And the outcome, the nominal outcome, is only 2 category. All right. If there are more than 2 category, we have different model. For example, the random forest for classification analysis. So random forest can be classification and can be regression. But we do not go through to that. We just use the logistic regression, okay, based on the quantitative variable to predict the outcome of nominal variable, which have only 2 categories. For instance, sex, okay, or origin, something like that. Just only 2 categories. We practiced yesterday. We use different quantitative variable to fit with the nominal variable called origin, right? So origin, we have the US origin and the non-US origin. So only 2, okay? All right. So today we focused on the logistic regression model fit, okay, and prediction. Okay, so prediction here, the most practiced way is to use or to reshuffle the existing data that we collect, okay, to differentiate to, or we can say to mix the order of the model. To mix the order of the sample. When we fit, okay, when we fit the model, the sample 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 until n, they learn that order 1 to n. But when prediction, we do not use the same order as we fit. We reshuffle the existing data so that all the data is mixed. So the model do not remember that, oh, this order of data is used in the fitting time. Okay, so that is the prediction. In other case, if you have a very good performance of the model, the logistic regression model during the fitting and the prediction using the existing data, then you can also use the logistic regression to predict the other outcome using different data set. Given that the performance of the model that use your existing data is good, okay, the performance is well, then you can use this well-performed model to predict the outcome of other data set, okay? But if your current model, the fitting and prediction using the same data set but just reshuffle, perform not well, then you could not, you don't have any justification to use your model to do prediction of other data set, okay? It is like a good practice of curriculum development, okay, or the agricultural practice, or like the ICT coding, something like that. If you have a good model, you can apply this model to the other area or to the other situation. For curriculum development, educational curriculum development, if you have a very good, well-recognized curricula, then it can be used by other countries. They can be adopted. But if the curriculum is not good, then no one will use us. I mean, no one will use our curriculum. It's the same in the model. If your model, based on the existing data, you are doing the fitting and prediction, it performs well, then your model, the current model, okay, can be used to apply in other data set. Okay, that is a meaning and introduction. Okay, right. So logistic regression here, the LR. So we fit and then we predict. All right, now let's go together with our R. Okay. So this is the R and some existing code that from yesterday here. Okay. So this is chi-square. This is a logistic regression. Let's make sure that we cover the logistic regression. All right. Okay. So the other level association between variables using logistic regression. And please remember, most of the time when we use LR or logistic regression model, the predictor, okay, are the quantitative independent variables, okay, are qualitative and binary. Okay, binary, just only two categories, all right? And the predictor can be one or more than one. If it is one, we call simple logistic regression, okay? If it is more than one, it is multiple, okay? All right. Let's run some code that we used yesterday, okay? So the code that we run yesterday, we want to predict whether or want to fit, okay? Or want to analyze. Fitting is like doing the analysis. We want to analyze whether the origin where all the cars are made or were made, okay, is highly depends on the price or not, okay? If it is a cheap price, the car will be or would be made in the US or outside US, something like that, okay? And based on what we are focusing here, we have a null and a alternative hypothesis, okay? Just a recall from yesterday. Price is the predictor, response is the origin. Please, any one of you, give me the null hypothesis of this one here. A0, okay?
There is no significant association between price and the origin.
Okay, so there is no significant association between, okay, between the price and origin of the car, right? Good. All right. And H1, there is, right? Good. There is a significant association between the price and the origin. And then, like we discussed yesterday, in order to be easy for interpreting, we need to convert, okay? Convert the origin, which is character, to number, all right? by using this code, the function if-else, right? Okay. You can also change. Yes is 1, it's fine. Okay. And no is 0. Let's say like that. There's no problem. What it is important if is the interpretation, is the result that you need to interpret the result. Okay, now I just change, okay? Change the non-US, I say yes. Those made in US is equal 0. They are still nominal, okay? Okay, I run. No, because there's some of the error here. Can you tell me what is the error? What is the problem? What is the cause of the error? I run the code on line 66 here. DF origin number, I append this new variable to the data DF. And there's an error message appears here. So what is the problem?
Maybe you haven't loaded the library, sir.
Okay, we haven't loaded the library, and as well as we haven't loaded the data. Okay, it says okay, in this appending, object of tag closer is not susceptible. It can't be subset, okay, because we don't have DF. So we need to run this one. Okay, all right. Okay, so DF is already here. Then we go to the line 66. Okay, I run. Okay, no problem. Then I want to check how many frequency, okay, how many counts of each category. 0 here, 48, 1, 45. 0 is, or 0 representing the origin. Where is the origin? 0 in this case.
Non-US.
0 here. Again, please.
Non-US.
So 0, I just change, okay? So all the data of DF region, if the sample is non-US, it is a yes. I replace by 1. If it is not non-US, I replace by 0. So 0 here is US or non-US?
No,
US, sir. US.
Right, it's you get to change from yesterday. Yeah, it is US. So non-US here, number 1. Okay. All right. So if you change, it does not matter. What matters is the understanding, is the meaning. So R, or in language, programming language, it's a trash in, trash out. For those who have studied ITC, information technology, you would understand. That's why in programming language, it needs to be specific, short, easy to read. Okay. All right. And no space if it is the code, something like that. Okay. Our model, the first model, LG1, we use GLM, the generalized linear family. Okay. Our response variables is the origin number, and our predictor is price. Okay. And the family of the GLM, okay, GLM family is binomial, meaning that our response variable here, okay, our response variable here is binomial. Okay, yeah, you can run now. Okay, LG1. Okay, and then we want to extract all the answers inside the model. We just say the summary. Okay, the summary here. And first of all, what you need to see first, okay, it is the predictor here, price, whether using our logistic regression, having a significant p-value or not. Based on the model, it has no significant, right? The p-value 0.336. 0.336. Is it significant? Significant or not?
Not significant.
Here. Not significant at all. Then we accept the
HO.
Right. We need to accept the null hypothesis, meaning that
there is no significant association between the price and the origin of the cars.
Good. Okay. So p-value equal 0.36, then accept the H0, meaning that no sig association between the two variable, the two bar. Okay. You just make it short, right? You can read it by yourself, or you can note by yourself. Okay. And inside the model, there are many results. You can say just name. We want to see all the names of the result, what it referred to. So there are many. Okay. First of all, the coefficient, residuals. Okay. Fitted value. The result from our analysis, the fitted value. Okay. You can see core. You can do the core between the DF. What is it? DF origin, okay, DF origin number, and the LG1 fitted value, whether any correlation. Okay, very small. See, very small, very small. Okay. All right. Because all the result, it does not show any significant association, then we do not need to do any prediction. Okay, just remember that if your preliminary analysis, or we can say your fitted model, do not show any significant result, meaning that result support the null hypothesis, if it is that case, you do not need to do further prediction by reshuffle the data. No need. Okay, no need. But if your fitted model is significant, meaning that the results support the alternative hypothesis, which is there is a significant association between the predictor and the response variable, then it is worth to do a prediction by reshuffle your existing data, or you can say by using cross-validation. I did not show here. Cross-validation, you use 1/3 of the data for fitting model and the 2/3 for validation or for prediction. Okay, that is another methodology when we do the modeling, but we do not go in that deep. We can just do the reshuffle of the existing data. Okay, another example is the weight. Okay, weight here. Okay, so weight, I first need to see a box plot here, just a exploration. If I do not run the logistic regression model, I would say there is no significant association between the weight and the origin of the car, because I see that there is a big overlap between the weight of car made in the US and those made outside the US, based on the box plot. But when we run the model, logistic regression model, okay, and do a summary, then you see there is a significant, and this is a negative, okay, the factor of x, okay, the factors of x is negative, like the factors of the LM model, right? Y equal this LM model, ax, okay, plus b. So here is the coefficient. It means the factors of x of the weight is negative, okay, it's negative. All right. Okay, so we can do some plot here. Okay, this somewhere here. Okay, yeah. Okay, and I would like to do another example, which results in a more or a higher significant value. Okay, another example using another variable. Let's say the RPM. Okay, I just want to check here. Names, DF. So here, I did some exploration last night, and I saw that the RPM here tend to have a more significant association between the car origin and this round per mile speed something. Okay. Okay. Okay, so LG, oh no, LG, yeah, logistic regression. It should be LR, is okay, equal GLM, and then you can say that DF number, okay, by DF RPM, okay. Then you need to include or just straight family, binomial, okay. Okay, I say it's good. You can just run here first. Okay, yeah, you can see here it's quite significant. Okay, null deviance and residuals is almost one by one. It's good. So if the null deviance and residual deviance is more or less equal ratio, our model is much better. If, like, for example, the null deviance is 108 and our residual deviance is 101, it's a very good one. Okay, so I can run this model. Okay, and then I do a summary of the LG3. Okay. Okay. So here is the result. Is there any significant association between the origin of the car and its speed, RPM? Any significant? Yes. Okay. Quite significant. 3 star, right? 3 star. 3 star. Okay. So here, 0.00015, something like that. Okay. And this is the coefficient. Quite small. The coefficient very small. 0.0002. Okay. Although it's small, but significant. All right. So it is worth to do prediction. Okay. It is worth to do prediction. You can do a plot first. It's okay. Okay. plot to see. Plot here. Okay. Yeah, it is quite separate. Okay. So number one, US or non-US?
Non-US.
Okay. Is it true? Yeah, it is non-US. So origin, yeah, it is non-US number one. Good. Still remember good. And 0 is US, meaning that the car made out of US, it seemed to have a high RPM, round speed per mile something. Okay. High. But for the US, some, not some, one or two. Yeah, one or two here is very high, while some other are small around here. Okay. So if you plot the model, a logistic line, please follow my mouse. Okay. It would be like this. Okay. Right. It is an increase. Okay. Because our coefficient is positive here. Okay. How about the previous one here? Positive logistic line or negative? The weight. Okay. The weight and the origin. The weight and the origin, our model, it has a negative coefficient. If it is a negative, then it will be a decreasing logistic regression line. Okay. And remember, it is not linear. Okay, not linear regression. And so the line is not or must not straight. It must be some like the logistic. Okay. Okay. So with this one, okay. Okay. So this is our graph. I take a snapshot and then I can put it in our PowerPoint. Then I can make a, okay. Okay. So here, okay. Then the line, the logistic regression line should be something like this. Okay. Oh no. Okay. 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 Should be something like this. It is the logistic regression line. The higher RPM value, okay, the higher the car should be made outside the US, okay, non-US, the origin. Okay. Most of the car, how many is it? How many data point? Okay. I'm not sure there's many. Okay. This is an example how the line should be. Okay. Now we can move forward how to do prediction and plot this kind of graph. Okay. In order to get a better illustration of our result. Okay. In order to have a better understanding, in order to make prediction, we should go to a more detail. Okay. Because when doing prediction, it needs a new data set. A new data set here, it means the data set from existing data set car 93 again, it just reshuffle, okay? Reshuffle, right? So we need to have some of the fitted value on hand, in hand, the standard, no, I mean the confidence interval in hand, so that it is good one, okay? Procedures to do prediction using the same but reshuffle data. Okay, the same data but reshuffle. But reshuffle. It's better for the meaning up. Okay. First of all, we need the RPM new reshuffle. We need a reshuffle RPM. So I say RPM reshuffle. Okay. Reshuffle RS reshuffle. Okay. Equal. So we can do some sequence. Okay. Mixing the sequence or the order of the data by using the function sequence. Okay. Sequence, right? Sequence generation. Okay. And we do the sequence within our data set, within our existing data set. So we sequence from the minimum data set of DF RPM, okay, to the maximum DF, maximum value of DF RPM, okay. How would we do the sequence? Okay, what is the interval, right? Okay, so sequence mean max, and then by here mean max okay, mark DF RPM, okay, minus the min of DF RPM, okay, and then here it is equal, okay, and then divided by the length of DF RPM, okay. Okay, so that is what we need to do. Just run the inside code here before we name it. Okay, it missed one. It should be something wrong here. So it should be this. We need this one. So
Sir,
yeah.
the by equals max DF RPM. RPM is small caps. It should be capital, I think.
Which one? Oh yeah. Okay, good. Okay, RPM. Okay, yeah. Run. Okay, now we got the results. Okay, so 92, 93, 94. However, our data set, how many sample? It is 93. So we got, okay, 92, 93, 94. So we need to minus 1. Take 1 out, okay? Okay, here 92 and 93, okay? So it is just a reshuffle data. You can take anyone out, no problem, okay? We have a new data set already here, okay? Yeah. Okay, all right. So this is our new data set that we can use to be the predictor of the origin, the new one. But it is still from the existing data set, okay? From the range of the existing data set. And we also need to find the fitted value of the model. We need to take it in order to compute the confidence interval. So the predicted value here, no, the model LG3 fit, okay, LG fit equal LG3, yeah, LG, and then fitted value, okay, predicted value. Oh, this is fitted value. We need prediction. Okay, prediction. I think we can do this is for loading the plot. Okay, prediction. So LG3 red, okay, equal. Okay, we just use the function predict. Okay, so we predict what? We predict our model. Okay, our fitted model. Okay, LG3 using our new data set. New data equal. So it need to be in the form of data. Okay, data frame. RPM. This is RPM reshuffle. Okay, so the model, our LG3 here, we use the RPM. Okay, RPM. So here is the RPM. Okay, all right. Okay, maybe we don't run yet here. Okay, I think RPM. Okay, RPM. Why? RPM. Yeah, we missed some other argument. So the types, we need a response. Okay, response. Okay, and then we need a standard error fit. We need true, and the show here RPM. I think we need to run the LG here. We need to form a good one. We need to put the data DF. We need this kind of formula in order to do the prediction. Okay, we run it again. Okay, and this one LG pred here. Okay, let's see whether is it true. LG3 new data is the data frame RPM. So in our LG3 we use RPM. Okay, and here we use also the RPM. So RPM here is RPM. Oh, come is not run. RPM.
Sir,
RS.
the RMP. RMP, I think it should be RPM, sir.
Okay. That's right. It's
the
hard
last
to
one.
see.
Yes, so that it will be
Okay,
right.
thank you. Okay, thank you. Okay, yeah, all right. Okay, so we can run now. Okay, yeah, all right. So we have already. Sometimes it's hard to see. Okay, the problem. It's just only one letters before and after. All right, so we can see this one. Okay, So we need the so the LG fit. So LG3, okay, LG3 fit, LG pred, yeah, from this and fit. Okay, you can see it already. So the fit here, it is the fitted value. We get already here all the fitted value. Okay, and we can see the upper line, SE upper line. Okay, standard error or confidence interval upper line. We have this one, LG fit here, plus this one is better, I think. Just take this one, easy. So plus okay, the LG 1 and SE fit, okay, and the SE lower line. So we have this one. We just take the minus. Okay, so okay, we have it. Okay, for this. Okay, good. And then we can already do some plot here. Okay, plot the DF, or let's say yeah, it's okay with the DF RPM. Okay, then DF origin number. Okay, and then you can see the this is the types of the data point. You can say like 10, and it is size of it, like say mostly it is 1, but we can say 1.2. Okay, and the YLab is the probability, and okay, all right, I think it should be okay. Yeah, okay. Oh, I forgot to put the color. Make it blue, maybe better. Okay, yeah, or maybe change the types of the data point. 16. Okay, it's better to see. So we need a regression line, okay, and also we need a upper and lower standard error so that we can see into what level it can be predicted. All right. So we can see the polygon here, polygon graphic. Okay, and we see the default reverse element, the RPM reshuffle. Okay, and then with the RPM reshuffle RPM reshuffle. Then we need to see the real one, the reverse with the upper line here. Okay, the line. Okay, so SE lower line. Okay, and this is C, so comma, and then so next one, and then the upper line. Okay, SE upper line. SE upper line. Okay, then we need the color. So here should I? So right here, this is correct. This one should be not. Should be somewhere here. Okay. So yeah. Okay. Another one is we need the colors equal like orange. Oh, let's say gray or orange. Okay, orange, and then we need border. Just don't need the border. Okay, I think it should be okay. So this is we need to build a polygons of around the logistic regression line. We use the orange. Okay, the polygon, right? Okay. All right, let's see. SE lower. SE lower. I will run this one. Okay, let's run this. Okay, and the polygon. Okay, here. So it's the standard errors, or let's say the confident let's say, what is it? The confident interval. Sorry, the confident interval of our prediction. It is not as that what I draw. So I draw here is really good. Not that 100% good, but it's better than what our model see here. Okay. Afterward, we need to plot our line. Okay. So we need to add the line. So lines, RPM reshuffle. Okay, RPM reshuffle, and then with the fitted value, it is the LG3 fitted. Is it from the above one? Yeah, here LG fitted value. Okay, and then the line width here equal to. Okay, all right. Oh, LG fit. I haven't run it yet. Okay, so okay, so you can change the colors. Okay, by yourself. You can do the red line or blue. Okay, this is the logistic regression line based on our prediction. Okay. All right. So if a 100%, or we can say the performance, the prediction is very good, then it should be something in between. Okay, the green here. So if it's good, this is a good one. Okay. Okay, the green one, if our model have this kind of pattern, the blue one, it is very good. It means the division between the 0 and 1 is quite distinct. If it is more flat, like the red is more flat, or let's say the black here is like this. Okay, sorry. Erases. Okay, let's say the black one. Okay, if it is like this, then our model is not really well in terms of the performance, meaning that the distinction, the predicted distinction between 0 and 1, or between the US and non-US, is not that well. There's not a real distinction. Okay, it is like in our model here. Okay, yeah. All right. You can also add the boundary. Okay, the line. Okay, the line of the lower lines of the RPM new, but we put with the lower line. I mean the lower SE. So SE lower line. You can see the line width. Okay, line width equal 1. You can use the colors equal gray. Let's say. Okay, can add. It's very small to see. Can put 2. Maybe better. Yeah, because it's gray, hard to see. You can say black or green. Yeah, you can see now. And the very first one, we can say gold, blue, to see the same as the data plot. Yeah. And the upper line, you can just copy the lower line and replace by the SE up. Okay. And the green color. So this is our model. Okay, our model. Okay. And if we want to see how much, okay, how much we believe that our model, the correct prediction, something like that, we can assess for using the Kappa statistic. There are many other my paper. Okay, where is it? What kind of the model? No, performance measures that you can use. So here, so you can find, okay, the different kind of measurement performance. Okay, performance of predictive model. I will show you. Okay. Okay. So this is the level of performance. The index is 0 to 1. 0 is the worst performance. 1 is the best performance. Okay, meaning that if the value of this matrix of this what is it, evaluators Kappa, it is 0, it means that your prediction has a 0 correct prediction. If it has a value of 1, let's say Kappa is 1, it means that every instances of your prediction is correct. If you have 100 sample, it means all of the sample will be correctly predicted based on the model. Another one to measure the model is AUC. Okay, under area curve, something like that, and another one is error rate. Okay. Among the three matrices, I use Kappa to assess our model, whether it has a good correct prediction or not. Okay. Or to what level we believe that our model is correctly predicted. Right. Okay. So in order to use the Kappa prediction, okay, using Kappa statistic to measures our LG3 performance. LG predict our model prediction. Okay. So yeah, in order to use the Kappa statistics, you need to install the library, another library. Library. IR. So this library is built with the function of Kappa statistic. Okay. So Kappa compute the Kappa stats. Okay. All right. Okay. For every one of you, if you haven't downloaded yet, please go to the plot panel here, the lower right panel, and click on package. Okay. And then click on install and type IR. Click on and install. Okay. But in case of mine, I already installed it, then I don't need. But for you, please do that. Okay. Do it before we move forward. Okay, everyone finish installing? Installing, finish? Finish, everyone? You got the mod, I mean the library?
Yes, sir.
Good. Okay, now, okay. Please remember that our response variables are nominal, and we convert it to 0 and 1. And because our predictor are quantitative, then the quantitative predictor predict the response variable in a form of quantitative data as well. You can see, like here, the LG3 threat, okay, value, okay, threat value, it is not 0 and 1, okay? It is not 0 and 1. It is in between 0 and 1. You can see the value here, right? Yeah, it is in between that. So we need to change, we need to convert using some threshold, okay? Here it is the fitted value based on our prediction, okay, here. Some value is nearly 1, some value are less than 5.5, some value are 0.2, 0.1, something like that, and some value is really small, 0.005, okay? So the threshold value, you can select. If you have a reference, you can also add a reference in your writing, in your thesis, in your publication. But if there is two category like that, like this, 0, 1, in most cases, our threshold to define 1 and 0 is the value of 0.05. If it is bigger than 0.05, we round it to 1, representing the non-US origin. Okay. If it is less than 0.05, then we convert it to 0, indicating the US origin of the car. All right. So we need to change the probability of our predicted value here. First, change, or let's say convert the predicted value into two categories, 0 and 1, using 0.05 threshold. Okay, threshold. Okay, so okay, we can say the threat probability, threat prop here equal our here, okay, LG fit threat here, okay, but we need to do the if else on this value, okay. So this is the value, then we need to do the if else. if else, okay, if our predicted value here bigger than 0.05, let it be 1. Otherwise, if not, okay, if not, it is 0. Meaning that, why is it like that? 0. Okay. If this value is, okay, smaller than 0.05, it becomes 0. If it is bigger, the first argument is yes. Otherwise, it is a no. A no equals 0 here. Okay. Then you can see, okay, 0, 0, 0, 1, 0, 0, 1, something like that. Okay. So we get already our predicted probability. Okay. Oh no. All right. Okay. Then our data frame, in order to compute the kappa, we need a data frame of our predicted probability and our observed probability. Okay. Our observed, okay, observed probability, it means our data 0, 1 is what? Our data that we use to do prediction. Observed probability is what? 0, 1. Our data that contains 0, 1 category is what? Is the origin, the data of the origin, 1 and 0. What is it? The F? The F what? The F? Any idea? The F origin number, because we convert it from character to number. And this is called our observed, or we can say the real data that we have. The real data that we have is the one that we observed, that we recorded from our observation. Okay, so that is, you can see here, yeah, 0, 0, 1, 1, 1, 0, something like that. Okay, we run. And then we need to have a data frame of the two. Okay, ops and predict. Okay, the data of observation and prediction together, we put it in the data frame. Okay, the pred prop and the op prop. Put the two vector. This is one vector. Okay, and this is another vectors. Okay, to be a data frame. Okay, now we have observed and predicted data frame. You see, for some data that are aligned to one meaning it is US or not US. Here, US or non-US. Anyone?
The number one, sir, is yes, non-US.
So non-US, right? Yeah. So our real data, sample number 1, 2, 3, 4, 5, it is the non-US, but our prediction, it is US, right? 0, 0, 0, 0. Yeah.
Yeah.
So the 1 to 5, there is a wrong prediction from our model is wrong. 6, 7, 8, 9, 10, something like that to follow until what? Until, wow, quite a lot. Until 38, they are correctly predicted. But from 39, a lot of wrong too. To 30, wrong prediction. The real is non-US, but it is predicted to be US. Okay. 51, okay, correct, because they are the same. 1 is 1 as well. Okay. Until 59, correct. 60 to 61, wrong, because the real one is US. It predicted to be non-US. So quite many instances that have wrong prediction, but the majority of right prediction is more than the wrong. So we can do the kappa now. Kappa, let's say kappa 2, it is the correct one we use. Okay, up and pred. Okay, then we can get the result. Okay, our p-value of the kappa is very significant, and the kappa here is 0.35. Okay, so it is like a moderate, okay, moderate correct prediction. It's below 0.5, okay, below 0.5, but still it is significant. Okay, kappa is 0.35, and when you have your data from the real observation, 0.35, sometimes 0.20, okay, like between or around 0.20 to 0.80, it is the most range that we can see from our real data. If it is up to kappa 0.9, 0.95, real data, we really have that value. It's rarely case. And most cases that we can see as well is the small kappa like 0.05, 0.1, 0.09, something like that. Okay, we can see many cases in our real world. But what we need to see whether this kappa is significant or not. Okay, so yeah, okay, kappa here, p-value equal 0.0006. So we can have a the alternative hypothesis accepted, okay, because it's this one. And our model is also significant, right? Our model, our fitted model. Let's see here, the summary here. Okay, also significant. And when we do prediction, it is also significant. Okay, all right. Okay, I hope you got some idea about the mixed method. We use quantitative to predict the qualitative data using logistic regression model. You can also, if you do survey in your data set, you can also use, like, for instance, whether the sex of, or gender, let's say, the gender of your employee or of your student or of your staff is highly dependent on the qualification, okay, or highly dependent on the period of the education, or highly dependent on the performance, their performance, okay. You can also make prediction. Some people say it is like a general hypothesis, general speaking. Men, okay, like high school student, all the boys are lazy. Just an example, not reality, okay, are more lazy. And therefore, their score, the final score of the exam, is generally lower than the girl student. All right. So we can use the score or the gender of the student, okay? That could be one possibility that you can use in your real research thesis or research project, okay? All right. Any question so far? Any things that we need to discuss before we're having a break? No? Okay, let's have a break then, right?